All right, guys. So our next topic was in our study of kinetics is collision theory and something called the Arrhenius equation. So we've mentioned this a couple times in class, but the rate constant of a reaction depends on temperature for one thing, and that's what the Arrhenius equation deals with. Before we get to that, though, we're going to talk about collision theory and kind of the current way we think reactions occur. And so, for what collision theory says, I think is really kind of straightforward and simple. It says that in order for a reaction to occur, molecules must collide. It's very simple. But when we look at that and we look at the frequency of collisions, we notice that a lot of the collisions don't lead to reactions. In other words, if every collision led to a reaction, we would expect the rates to be a lot faster than they actually are. And so, what we found out is that it's not only enough to collide, but there's like an energy barrier. So when these collisions occur, they have to collide with enough energy. But even taking that into account, you can look at something called the Maxwell-Boltzmann distribution, which we've seen before, and we'll look at again here. But even if you take into account the number of collisions and then like the percent of those collisions that have enough energy, you still get a rate very, very often slower than you would expect. And that comes from the fact that these collisions with enough energy also have to occur with the molecules in the correct orientation. Okay, and so there's three things that go into setting the rate of reaction. One, how frequently they collide, kind of the percentage of those collisions that have enough energy to form something called a transition state, and then are they approaching each other in the correct orientation, in the correct way to form this transition state? So, I mentioned a transition state, and you can kind of see it right up here. And so this is the vision. So if we take a reaction, we have BRNO, and we have two of them reacting together in kind of a decomposition, type of thing here. The idea that we have is that there's something called an activation energy. And so you can kind of see it right there. The activation energy is the energy that you need, or that the molecules need, in order to form this transition state. The transition state is a very short-lived state. It wasn't until kind of the later half of the 20th century that we were able to actually kind of see this in real time, and we can finally do that using ultra short, fast laser pulses, assuming the transition state absorbs those colors of light. And by ultra short, we're talking like on the femtosecond, maybe picosecond time scale. Okay, but anyway, we can see the transition state now. It's very short-lived. You can't bottle it up and store it, and it forms on the way from reactants, over to the product side. Okay, and so when these collisions occur, they have to occur with enough energy, this activation energy, and we've seen this diagram before. So that's the energy of the reactants, and this would be the energy of the products, and then there's this difference in energy between the two. And so when you think of this is maybe the forward activation energy. There's also a reverse activation energy that would be going from here all the way up to there. And so you can say the activation energy for the reverse reaction would be kind of the sum of the change in energy plus the activation energy for the forward reaction. Okay, so very often you'll get a question saying, hey, here's the activation energy, maybe here's the change of enthalpy that occurs. Very often delta E is given as a change of enthalpy, and they want you to figure out what the reverse activation energy is, or vice versa. And to do that, I suggest you guys draw this out. This is a reaction diagram. So we have energy on our vertical axis, and this kind of reaction progress. So this is loosely analogous to time. So as the reaction progresses, it goes from reactant to product. Okay, and then we symbolize the transition state. This is a pretty straightforward reaction. You will have some where we would maybe have an intermediate, so it forms one transition state, and an intermediate, then another transition state before going back down. So these can be fairly complex. Okay, but this is the activation energy that we're talking about, and as we'll see in a bit, it's why temperature has this effect on chemical reaction rates. Okay, so as I said, it's not enough just to collide with enough energy. It's not enough just to collide. It's not enough to collide with enough energy. It has to be the proper orientation. So for the reaction that we're just looking at between the BRNOs, you see here that if they kind of approach side by side and they collide, that's going to be a proper orientation. But if you look at B and C here, they can knock into each other. If the two bromines knock into each other, that'll work. And then, but if the oxygens knock into each other, no reaction is going to happen. Okay, and so there's going to be a certain percent of collisions that occur with this orientation. So even though they may have like gobs of energy and they're colliding, if they're not pointed in the right way, then there's not going to be a reaction, and our reaction rate is going to be slower because of that. Now, this occurs very often with more complex molecules. So you'll see it in organic chemistry when you guys study organic chemistry in college. It comes up. It's called steric hindrance. And then you can imagine like biological molecules, like these ginormous molecules, how hard it is sometimes to get them oriented the right way, which is where proteins and catalysts and enzymes come in. So we'll talk a little bit about that. But yeah, so this idea of steric hindrance of, it's kind of hard to approach in the proper way sometimes will slow a reaction down and lengthen the time it takes for it to occur. Okay, so looking at these factors that affect reaction rate, we have concentration, we have temperature, and then we have the presence of a catalyst. The concentration, I think, is easy enough to understand. So the higher the concentration, the more the collisions. Okay, so the higher the concentration, the more collisions occur. Okay, and that's a very straightforward way to understand why more collisions occur. Yeah, that's a fairly straightforward way of understanding, and so therefore the reaction rate increases. And there's different ways to do this. This is why we dissolve things in solution and why they occur more quickly rather than just having it occur on the surface of solids. It's why when we have powders and we increase the surface area exposed, more collisions occur. That's a way to increase concentration in a lot of ways. Okay, so I'm not going to kind of belabor that point anymore. Now, temperature, this again is tied to the activation energy. This increases the number of collisions with enough activation energy. So increases number of collisions with the activation energy or greater. Okay, and to understand this, we can look at our old friend, the Maxwell-Boltzmann distribution. We talked about this when we talked about the kinetic theory of matter, and a little bit about gases. And this idea that you can plot the number of molecules versus energy. In this case, it's the number of collisions versus energy. And as we increase the energy, there's a shift in this distribution. So T2 is greater than T1 here. There's a shift in this distribution. So if it requires this much energy to react, the area under the curve gives you the number of molecules, essentially. And so at a higher temperature, there's just a larger area. Okay, you have this additional area, so you have more collisions occurring with enough activation energy, and that increases your rate. Okay, so I should put here to be more specific. Higher temperature, okay, increase the number of collisions with the activation energy greater, and will increase the rate. Okay, and increases rate. Okay. I want to go to this slide. And then finally, we have the presence of a catalyst. Now, the presence of a catalyst, so a catalyst is something that allows the reaction to go more quickly, but isn't used up itself. And so to show you the difference between these, I'm once again going to do energy versus reaction progress. Kind of looking at that diagram for the previous slide. So say that there's an uncatalyzed reaction, and then it kind of goes like this. Okay, so there's our reactants, here's our products, here's our transition state. Okay, and there's a certain activation energy required to get to that transition state. What a catalyst does is it forms a different transition state very often. Okay, so maybe this is the transition state with a catalyst. Okay, so what a catalyst does is it provides an alternate pathway for the reaction to occur. It's like a different reaction mechanisms, essentially. Sometimes it's like, maybe different intermediates, but sometimes it could be like structural, just holding them in place, the proper orientation. But there's a different transition state that occurs, which has a lower activation energy, which essentially is like taking this and shifting it to the left there. Okay, so that's why a catalyst works the way it does. Is it increases the rate of reaction. Next chapter we're going to see, although it does that, it doesn't change like once the reaction is completed what the concentration of everything is. Okay, but it provides a new path for the reaction to occur. Okay, so this brings us to the Arrhenius equation. As I said, temperature has an effect on reaction rate, and we've said previously in the course that the rate constant depends on temperature. This is the equation that tells you what that temperature dependence is. So this K is our rate constant. Okay, so this is the rate constant in our rate law, and we also see it in our integrated rate law. E sub A is our activation energy. Okay, R is the gas constant, but we have to use it in SI units, so 8.314 joules per mole Kelvin. We have to use that value, and then T is the temperature in Kelvin. Okay, so we call that the absolute temperature, right? Not sure why that freaked out like that, but this is the temperature in Kelvin. Okay, and then A is something called a frequency factor. We don't really have to worry too much about this, but I want to explain a little bit because it's in the equation. This frequency factor, it's a combination of the number of collisions that are occurring and the number of effective collisions that have enough energy in the proper orientation. Okay, so that's what both those get kind of combined into the A. And we could rewrite this as natural log of K is equal to natural log of A minus EA over R times 1 over T. And I'm going to write it this way because it gives us an experimental way to get the activation energy if we so chose. And so the way it does that is if we take this equation and we were to plot natural log of K, which is kind of our Y here, this is going to be our B, okay? This will be our M, and that will be our X. Okay, so if we have K's at different temperatures and we plot this versus 1 over T, we would get a line with a negative slope. This slope will be equal to negative EA over R. Well, since we know what R is, that's always 8.314 joules per mole Kelvin. This is a way to experimentally get this activation energy. And I think that is just awesome, awesome, awesome. Okay, just by measuring these Ks, we could use by concentration versus time using integrated rate law, we could use method of initial rates. If we change the temperature, we get Ks at different temperature. We can plot them, and we can actually find something out about the energetics of the reaction of that transition state in the rate determining step. Okay, so this is the temperature dependence, and I think you guys have one homework problem that asks you possibly to find the activation energy. They give you K and temperature data. Okay, so that's it for this video. I hope you guys took good notes, and if you have any questions, please let me know.